In this section, we're going to learn how to calculate standard changes for enthalpy, entropy, and Gibbs free energy. So first, of course, just definitions. Let's talk about what standard changes mean. Standard changes are just changes in each of these quantities when all reactants and products are in their standard states. Okay, what's a standard state? Really simple. These are just arbitrary conditions that chemists picked so that we could have a comparison point when doing the same reaction in different laboratories. Delta H, delta S, and delta G are all very sensitive to temperature, pressure, and concentration of your reactants and products, and therefore we just wanted a nice standard set of conditions for easier comparison. So we picked some really easy numbers. For a gas, it's a pure gas at a pressure of 1 atmosphere. For a liquid or a solid, it's the pure substance in its most stable form at a pressure of 1 atmosphere. So if you remember back to phase diagrams, if you looked up at a particular pressure and temperature, you would find if it's most stable as a solid or a liquid. So that's what it's really referring to. What's it most stable as? And for something dissolved in solution, it's a concentration of 1 molar. Most of the time, it's implied that the standard state is 298 Kelvin. Occasionally, you'll see it for 273 Kelvin, but 298 Kelvin is a little more common. So that's typically what we assume. So that's what my standard states are. And for the standard changes, all I do is I look up the standard enthalpy, entropy, or Gibbs free energy of each of my reactants and products, those individual molecules. I add them up for my products, I add them up for my reactants, and I subtract. And that's going to give me the delta H, delta S, or delta G for my overall reaction. Super easy. This N here just refers to how many of that each particular molecule you have in your chemical reaction. So if you have 2, you'd have to multiply its delta H by 2. And this guy here just means add. So we're adding up everything for the products, adding up everything for the reactants, and then we subtract. Love these problems, super easy. So let's look at an example. Calculate delta S, delta H, and delta G for the following reaction using the information provided. So we usually get this nice little table, and we get a chemical reaction here. So we say, all right, we'll start with delta S. So we'll be using this column right here. And I always just abbreviate this equation with delta S equals products minus reactants. This is how I write all of them. I'm going to add up the stuff for the products, add up the stuff for the reactants, and then I'll subtract. So for the products, that's my NO2. So that's this guy right here. And I got to keep in mind that there's 2 of this. So there is 2 of my NOs. Oop, I'm sorry, yeah, 2 of the NOs. There's no NO2. I'm saying it wrong. So I'm going to take 2 of my NOs, each of which are 210.8 joules per mole Kelvin. And I'm going to subtract. And now I'm going to add up my 2 reactants, which are 191.6 plus 205.2. And both of these are joules per mole Kelvin. And because they each had a 1 in front of them, that's why I didn't have to multiply them by anything. They're just multiplied by 1. So now I just do that math. 2 times 210 minus these guys, add it together. And I get 24.8 joules per mole Kelvin. So we don't neglect our units. Sometimes I see people leave it off in here and then tack it on at the end, and that's fine as long as you tack it on eventually, but you can always find your units up here. That's the units you should end up with. So that's delta S. We're going to do the same thing for delta H. So again, we're going to use this idea of products minus reactants. So my product is NO. So that's going to be 91.3. So I remember 2 times 91.3 because I always use that stoichiometric coefficient. And now my units are kilojoules per mole. And now delta H is really easy. Delta H for any molecule or any element by itself, like N2 or O2, it's always just 0. Super easy. So I'm going to do minus 0 plus 0. That's nice. And so really I'm just doing 2 times 91.3, so I get 182.6 kilojoules per mole. All right, now I seem a little stuck. We say, okay, we did delta S, we did delta H, but I'm also supposed to do delta G, And that is not in my table. Now, if they had provided delta G numbers in my table, I would do the exact same thing I've done here, just do products minus reactants. But sometimes we like to make you use more than one concept at a time. So now we can look at this and say, oh, wait, I have delta S, I have delta H, I know exactly how I'm going to get delta G. Oop, it always erases the second part. So we just said our delta H is 182.6 kilojoules per mole. So anytime we have a delta S and we have a delta H, we can very easily get a delta G by doing delta H minus T delta S. And if we plug in the standard delta H and the standard delta S, that'll give me the standard delta G. So life is easy. So my delta H is 182.6. And I always have to watch my units. This time I'm going to stick with kilojoules just for variety. So I'm going to do kilojoules per mole minus, now my temperature, again, I said we most of the time assume that's 298 Kelvin. So even though it didn't explicitly say that, we're going to assume that because these are standard conditions. And this time I'm going to convert my delta S into kilojoules. And that's because delta G is usually reported in units of kilojoules per mole. It doesn't really matter as long as you're consistent, but just for variety, we'll show how to do that one. Really easy, just like you multiply by 1,000 to turn kilojoules into joule, we divide by 1,000 to turn joules into kilojoules. So I'm just going to do 24.8 over 1,000, and now that'll give me kilojoules per mole times Kelvin. So my kelvins will cancel and just leave me with kilojoules per mole on both sides. So I just plug that into my calculator, 182.6 minus the product of 298 and 24.8, and I get 175 kilojoules per mole. Again, if I had had delta G in the table up here, I could have just done that whole products minus reactants trick, but because I didn't, I just used my very handy equation we have here. And we can always look at it and assess. We have a positive delta G. That means this reaction is non-spontaneous under standard conditions. It didn't ask us that, but I always like to just think about that and remember why we're interested in delta G.